There's this work of Kuzma and Thorngren, follow-up work of Thorngren and von Karasling. There's one of the papers of Wang, Wen, and Witten. There's some stuff by Yuji Kajikawa, plenty else, mostly in the bosonic case. And then people have done some generalizations to the fermionic case, but typically what you'll see is maybe they're restricting which possible, like of the possible spin invertible field theories, they're saying, well, I need these restrictions before I can even ask the question. Or maybe they're looking at low dimensions or such. So of these references, I want to highlight the paper of Cordova and Omori. Actually, I guess 2 papers, because our proof of non-existence is heavily inspired by those. So when it is not possible to do this, our proof was based on those. There's some work on higher symmetries. And like I said, there's a lot of stuff based, like removing the assumption that alpha is invertible that I was not able to list here just due to space reasons. So check out these papers and more. And now I want to talk about the theorem that we proved. So we are restricting to the setting, like I mentioned, finite group acting on a 4-dimensional fermionic theory. And I'm going to restrict to the case where G acts unitarily, but it is allowed to mix with fermion pairing. So in this, within this setting, there's a nice class of invertible field theories built from something called twisted supercohomology. Now, people mean different things when they say supercohomology. Do you want the supercohomology of a point to have be non-trivial in 2 degrees or in 3 degrees? I mean the latter. So this is a thing built by, for example, Wang and Gu, and maybe a few other authors, not the earlier one from about 2012. So if you have a twisted supercohomology class, you can build an invertible field theory similarly to how Fried-Quinn defined classical digraph-Witten theory. And the supercohomology class is the action. So what we showed is a 5-dimensional invertible field theory is the anomaly of a 4-dimensional unitary topological field theory with the assumption on the dimension of the state space of the 3-sphere, if and only if it's one of these supercohomology examples. So we realize the supercohomology ones, and there's a nice obstruction to being able to be a supercohomology invertible field theory, and that's also the obstruction to being the anomaly of a topological field. Yes.
How many layers? I don't know how many layers. Yeah, that's ambiguity.
In supercohomology?
Yeah.
3 layers.
3 layers.
Yes. Yeah. So for all invertible field theories, there's 4 layers, and so we're saying the first 3 are fine, the 4th one is the problem. Yeah. Thank you. Who else has questions? Okay. Before I say this precisely, I should. Oh wait, yes. Sorry. That was on the first slide. So to say that Z has an anomaly alpha is to say that Z is a boundary theory for alpha and alpha is invertible. Was that a useful answer? Okay. If you'd like to talk about it more afterwards, just let me know. More questions? Yes.
So when the 5D invertible theory is not an anomaly of a 4D, it could still be the anomaly of some gapless forest.
I guess the question is, what's the difference between gapless theories and topological field theories, or like and things which I don't feel qualified to comment on. Oh wait, gapless, not gap. Sorry, you're absolutely right. Okay, yes, and so in fact we expect that in a lot of examples where you write down some explicit quantum field theory and you say, oh, what's the anomaly? Okay, the obstruction is non-zero, therefore it's still the anomaly of the original quantum field theory we started. Did that address your question?
Well, but you do expect the 5D invertible theory, any 5D invertible, to be the anomaly of some.
I think so, yes. Yeah, it's a question of whether I get it gapped. Okay. Yeah, sorry for my confusion earlier. Who else has questions? Okay. So first I want to talk about what symmetries I'm looking at. So let's say I have a group acting on a spin manifold, and let's say that this action is orientation preserving. So to say how it mixes with the spin structure is a non-trivial question. For example, I can act on the manifold consistently, but only projectively on the bundle of spin fins. So instead what you've got is actually there's an extension by the spin fin, which I'm just writing as plus minus 1. And so if you take the quotient, sorry, I should have said the quotient by the quotient manifold by this free G action, it doesn't necessarily have a spin structure. It has this generalization of a spin structure where you don't quite have, it doesn't quite close up. You have to add this extra G tilde symmetry to sort of close everything. So for example, if G is U1, this would be a spin C structure. But you could do this for more general groups. So my favorite example is the K3 surface. And I said the K3 surface because I'm not an algebraic geometer. If you are an algebraic geometer, there's many, but they're all topologically the same. So, and it admits a free, smooth involution, but this involution does not lift to the bundle of spin frames. And so the quotient, which is called the Enrique surface, does not emit a spin structure. Instead, what you have is this thing frequently called a spin Z4 structure, which is like spin C, but the U1 has been broken to Z4. And that's because I can lift to a Z4 action, but the even numbers inside Z4 are the same as plus minus 1 in spin. So you get this quotient, and you get this structure on the Enrique surface.
All right.
What's up?
Let's compress the non-fields on sort of geometry.
I think that's a good way of thinking about it. Yeah. It's like you want it to close up to spin times Z2, but it's anomalous. In the sense that like it's projective, I'd say that, yeah, that's correct. Yeah, good. Who else has questions? So I'm going to refer to this a little bit differently. I'm going to refer to this in terms of cohomology. So the double cover is classified by a degree 2 cohomology class, which I'll call B. And so I'm going to refer to this as a BG, B twisted spin structure. It's like I have a spin structure, but I've twisted it by this double cover. So let's talk about an analog of this in the context of symmetries of field theories. So if I have a unitary symmetry of a fermionic unitary field theory, there's the question of how does this mix with fermion parity? And so I think Cameron talked about this a little bit, but in general, what you need to do is you need to specify an extension of your symmetry by fermion parity, which is a plus minus 1. So we have exactly the same data matching up. We have a double cover. And I think the cleanest way to say that, what it means to have this symmetry with this particular way of mixing with fermion parity is to say, I extend my field theory from spin manifolds to BG, B twisted spin. So you may be familiar with this in the context of spin C structures, where you have a U1 symmetry, except U1 only acts projectively on the fermions. What you've actually got is this, the double cover U1 acting on fermions. And so if you want to put that on spacetime, you need a spin C structure rather than just a spin structure of U1. So the goal here is to do this in more generality. So the theory and its anomaly should have matching symmetry types. So I'm looking at BG, B twisted spin invertible field theories. And now that's something we can classify using homotopy theory. So let me revisit the theorem that Fried, Hopkins, and Grady proved and say it a little more precisely. So I kept saying it's homotopy theory. So what homotopy theory have we got? So I want to study the abelian group under stacking of n-dimensional twisted spin invertible field theories for G and B. And the claim is that this is the same thing as the I appear to have made a typo. This should be cohomology group of a point for this thing called the Anderson dual of the corresponding BG-B twisted spin boards. So if you like spectra, you take the spectrum of BG, B twisted spin boardism. That's a Thom spectrum. You take its Anderson dual, which is the thing you do to spectra, and then you take the cohomological point of that. If that's not your jam, you can think about this as follows. Take the boardism groups, so BG, B twisted spin manifolds, modulo those that are boundaries. And then what you do is you do something which is the opposite of the universal coefficient theorem. So in the universal coefficient theorem, your torsion summands move around and your free summands stay in place when you go from homology to cohomology. Here, what we're saying is you leave the free summands in, move the free summands down and shift the torsion summands. So there's good reasons for doing, there's physics motivated reasons for doing this that I don't want to get into for reasons of time. If you're curious about this, let me know and I'd be happy to say more about it. But the point is, if you know the boardism groups, which we have ways of computing, then you can read off the groups of invertible field theories by a reasonable, if strange, local procedure. So, okay. I wanted to call this upside down omega, which I saw in the paper, and I want to talk about why I did this. So homology is written with the right side up H, and cohomology is dual. So you're writing with an upside down H. So Bordism is written with the right side up omega. So invertible field theory is generally written with upside down omega. So I will, and we've seen this notation, I mean, also in Cameron's talk, and I did not invent it, but this is why I like it. What's up? So you can, I want to say it's stacking. If that speaks to you, then good. If not, so the invertible field theory, it's a functor to complex vector spaces. So I can apply tensor product to the vector spaces. I can tensor the morphisms, etc. Yeah, but these are the anomalies. So you can stack. So I'm saying stack the anomalies. I'm not worried about the boundary field theories right now. Did that answer your question? Cool. Who has more questions? Okay. So what is twisted supercohomology? So I like to think about this from a homotopy theory point of view. So if you have a spectrum or if you have a generalized homology theory, the first piece of information about it is what do you get when you apply it to a point? So that's the list of homotopy groups. And there's a process called post-Minkowski truncation where you say there are too many homotopy groups. I'm just going to turn the ones in high degrees to 0. So if you do this to spin Bordism, you get a thing which is, well, it's what it is. But then the Pontryagin dual is this thing called called extended supercohomology. And so, okay, how do you incorporate the twist? There's some stuff to do there, but it's not that much more complicated than what I said. You got the key idea, and you get this thing called twisted extended supercohomology. So this has been studied from a couple different points of view. Wang and Gu, I think, were the first to write down a definition. Kapustin and Thorngren also wrote down a definition. And looking at the timeline and realizing they were at the same time. So first is maybe I need to go back and double check. And then Thibaut Descoupé, who you will hear from tomorrow at this conference, has a definition of twisted supercohomology from a more category theoretical point. So these are different ways of thinking about the thing that I'm used to thinking about homotopically. And one thing which I mentioned Pontryagin dual, and I mentioned Anderson dual in the context of invertible field theories. So these are not the same, but since we're only thinking about finite symmetries, they're going to be it's going to be equivalent. And so if this detail is flying over your head, then everything is okay. And if it is not flying over your head, then I'm trying to reassure you everything is okay. So technical detail, annoying, not important. So I want to get a map. I want to get a map from supercohomology invertible field theories to all invertible field theories, which is sort of the thing which says, okay, I have a supercohomology class, I get an action. So how do we actually define the map? Is you take the post-Minkowski truncation map from spin Bordism to the post-Minkowski truncation, hit it with Anderson duality, and that right now that's fine for the setting we're working in. That we can work with Pontryagin duality. So this is the map that takes a supercohomology class and produces an invertible field. Okay, sorry, that might have been a little convoluted. We're not going to do that much more homotopy theory. So now I can say the main theorem precisely. Pick a finite group, pick a degree 2 cohomology class, or equivalently a double cover, and pick an invertible field theory in 5 dimensions on manifolds with the BG, B twisted spin structure. So then the following are important. So the first thing is there is a TFT with this anomaly. There's a typo here. I should have put unitary, but like in the other part of this file. And then we have the assumption about the dimension of Z of S2. So you can find a topological field theory. Equivalently, there is an algorithmic construction of such a topological field theory. We were quite surprised about this fact. Equivalently, the extremal layer in the Atiyah-Hertzberg spectral sequence of this invertible field theory vanishes. So like I said earlier, we've got 3 layers that are fine, and it's the 4th layer that's a problem. So I will show a picture later that says something about this. And then equivalently, the partition function, so the action of this thing, is a twisted supercohomology class. So in other words, either it's twisted supercohomology and you can realize it, or It is not twisted supercohomology, and you cannot realize it. And in fact, when you can realize it, you can algorithmically construct the boundary topological field theory. So what I'm going to do next is I'm going to talk about the, depending on how much time I have and how that goes, I want to talk a little bit about the existence part for supercohomology and a little bit about the non-existence and when it's not supercohomology. And but before that, has anyone got any questions? Yes.
When you show like your mathematical theorem where TFT means fully extended coherent TFT, it means unextended means what is the math word that it means TFT in this theorem?
Great. So what does TFT mean? It's too mathematically precise, and that different people mean different precise things by topological field theory. I mean fusion two category. Yeah. So in general, there's a construction of four-dimensional topological field theories by Douglas and Reuter, which takes in an algebraic object called a fusion two category, and that's the setting in which we were looking at topological field theories.
And so you're somehow implicitly assuming that every 40 TFT is a Douglas-related type?
Is what?
Is a Douglas-related type?
I guess, yeah, that is implicit in my assumption here. Yeah, thank you. Yes, definitely.
Yes, maybe in that concept, I use maybe like which invertible guys and Python or maybe like spin fixed points of Python, which of those have morphisms to trivial thing?
I don't feel confident answering that exactly right in front of everyone, because I'm not used to thinking from that point of view. But can we talk about this more afterwards? Yeah. My guess is the answer is yes, but put some pretty big grains of salt on it. So wait, your question was if there are like, wait, so if you want to replace S3?
Yes.
I have not thought about that at all. That's a good question. I don't know what to expect. Yeah, good question. Sorry, I haven't really answered.
So like the said that the 40
Yes, so fusion, given by the ones obtained from fusion two categories by Douglas Reuter. So maybe the question is, how's the state sum defined? Okay, if I'm thinking. So the thing is, another possibility is this something to do with the G symmetry? Because like as just a spin TFT, there's not really room for there to be an anomaly in dimension 4, because there are no 5-dimensional invertible field theories on formation. But now we introduce this G symmetry and we have an anomaly. So is that the thing where it's like just on spin manifolds with trivial principal bundle you don't see the anomaly? Is that?
Yeah, I was just my impression is that state sum stuff. Well, at least it's more interesting.
Where's the juicy representative thing on the site?
I do not know.
So it's let me ask another question.
It's not just it's not just a state sum. State sum that's got to go back and be the way those develop.
So you have a state sum on top. You have
Yes. Okay.
okay.
Thank you for rescuing. Yeah.
There are like 3 different layers of what like first layer is there has to be anomaly different level. Second layer is actually of the anomalous theory or boundary. Third layer is the anomaly of the underlying or knowledge field.
So okay, let me see if I've repeated your question correctly. Your question is there sort of like 3 layers of this? One is the anomalous, the invertible field theory itself, then the anomaly theory, then something more geometric. Is that? Yeah. I don't know. I have not thought much about that 3rd layer. So I'm not really sure how to answer. Again, I'd be happy to chat about it afterwards. I just don't know exactly how to right now. Sorry about that. I thought it was, yes.
If there's a physics law that typically any anomaly can be realized in a easy broken things. So if you restrict this, if you relax this restriction on the sphere, you expect to be able to realize everything. This is still some restriction.
That's a good question. So my gut feeling was to say that topological field theory is really strong already, and so like I feel like it seems reasonable to say I can produce a quantum field theory out of that. And then a topological field theory is really strong. But I'm wading into waters I feel I'm not used to swimming in. So I want to say it should be like this dimension of Z of S3 assumption is not carrying a lot of weight, but I worry that I'm wrong. So yeah, sorry, that's a complete non-answer, but I'm hopeful that this assumption is ultimately removable.
I would exclude this. Thanks.
I'm not sure. So, yeah, we can chat more about that. Yes.
You want to have a classification of find the invertible, chromatic invertible topological theory. Or your result will not be part of this classification.
Oh, I'm assuming the Vorticel classification. I'm using the Vorticel classification.
Vortical, I see.
Yeah, so that's how I got the 4 layers, is because from the 4 Vorticel groups that are non-zero. Yeah. Okay. Other questions? Surely there's another question out there. All right. Yes, and so
You have about 12 minutes.
12 minutes. Okay. Thank you. So another takeaway I wanted to mention is if you have an explicit example you want to look at, okay, there's an obstruction to compute that has to do with the Atiyah-Hertzberg spectral sequence. And I know different people have different feelings about this thing. But I want to tell you, I think this obstruction is not just tractable, it's also fun. And so I encourage you to go out and do some examples. Speaking of examples, so there's the prior work of Cordova and Omori, and then we gave some examples, and then Zheyan Wan, Zhuwen Wang, and S.T. Yao wrote some papers more recently that also did some examples. And I want to mention their papers specifically because they construct, like, in an example where the obstruction vanishes, you can ask, do you have the most efficient construction of a topological field? Is it smaller in a rank sense? And their constructions are our examples are not optimized and theirs are. So I wanted to point out that. So let's actually talk about an example. So we'll start with a 4-dimensional gauge theory with G is your gauge group, and you have a bunch of fermions, and they transform into a representation of the gauge group. So I'd like to be able to rotate fermions, but the ABJ anomaly breaks the U1 symmetry that does that to a cyclic symmetry of finite order with some formula. And the order 2 element in this group is fermion parity. So we have a twisted spin structure. And if we want to realize this, we need twisted supercohomology. So this thing can still carry an anomaly coming from the fact that we have a fermionic field theory. And so we might ask, okay, in an example of interest like SU2, what can we say? So let's say that the representation is the 3-dimensional one. This is a nice friendly thing. So we have to compute what is the group of invertible field theories, and it's Z32 plus Z2. If you like the phrase spin Z8 orism, this is that. And this was computed by Xie some years ago. And the obstruction, the thing that I'm calling the P plus IP layer, takes your Z32 class and reduces it mod 4. Okay. So what's the anomaly of this gauge theory? Oh, it's 22 in the first degree and 0 in the first sum and 0 in the second. So 22 mod 4 is notably non-zero. So you cannot realize this thing by a topological field theory, where I should have put the other adjectives, unitary Z of S3 is 1-dimensional. So this is I don't know. I liked this concrete example. I was hopeful that there would be a topological field theory, so maybe I'm a little sad. So okay, plan B. Let's talk about the odd-dimensional special orthogonal groups with the standard vector representation. Yes.
Sorry, confused. Is G a global symmetry here?
Yes.
Okay, so you don't really mean gauge theory.
Wait. Oh, sorry. No. G is the gauge symmetry, and then the global symmetry is this Z mod 4 NF delta, which ultimately came from the ABJ anomaly. I'm so sorry. Yeah, thank you. Okay, so maybe we can hope to get a better example. So let's do SO2n plus 1 in vector rep. And now we have a Z4 symmetry floating around. And again, 2 in Z mod 4 is fermion parity. So this is the group this is spin Z4 boards in 5 dimensions, which is Z mod 16. So Giambalvo computed this Bordism group in 1971. He was not thinking about invertible field theories, but I like this paper because it turns out, like 40 years later, it turns out this is exactly the Bordism group we need. And it was our. So that made me very happy. So the P plus IP layer sends a number mod 16 to the same number mod 2. Now, fortunately, the anomaly of this particular gauge theory, okay, it depends on n, but it's always even. So its P plus IP layer vanishes. And this anomaly can be realized by a topological field theory. In fact, a Z mod 4 gauge theory, which does not follow from what I told you so far. So is this saying that the Z4 gauge theory is in this phase diagram for this gauge theory? I'm not saying that. All I'm saying is that it's possible that this has a, that to realize this anomaly with a topological field theory. Again, with the dimension of ZFS3 and the unitary. So this example does work. Okay, so I am going to skip the proof of existence. And the reason I'm going to skip it is that the thing that we're going to use is what's called a symmetry extension construction. And the particular form that we use is due to Thibaut Decopé and Matthew Yu, who are both here. And in particular, this is the paper that Thibaut is planning to speak on tomorrow, if I understand correctly. So you'll hear all about this tomorrow, and therefore, given that I have to cut something for time, I'm going to cut that. But it's a okay, so symmetry extension. I apologize for this. And oh yes. So then I want to talk about the non-existence thing. How much time do I have?
7 minutes.
7 minutes. Oh, good. Okay. So I want to talk about the obstruction. And so, like I said, the obstruction is if you lay out this group of invertible field theories in the Atiyah-Hertzberg spectral sequence, it's just the top layer. So I want to say something about what that looks like, and then how did we prove it? And again, our proof is really Cordova and Omori's proof. So how did they prove it? So we're going to use the Atiyah-Hertzberg spectral sequence, henceforth AHSS, to produce this obstruction. So the Atiyah-Hertzberg spectral sequence, like all spectral sequences, it's an approximation. So I want to compute the group of invertible field theories. Well, what would be the easiest way for this to work is to say that this generalized cohomology group is just an ordinary cohomology. And so this ordinary cohomology group is easier to compute. But then the question is this actually the correct answer? Usually it isn't. But the point of the spectral sequence is you can start at the wrong answer, apply a sequence of corrections, and arrive at the correct answer. So we're going to do that approximation, and we're going to use it to define the obstruction. So if we're in dimensions 6 and below, then the only places Q can be non-zero, so the data fed into this direct sum, is -1, 1, 2, and 3. And this is ultimately due to a computation of spin-Bordism due to Milner a long time ago. So the P plus IP layer, the obstruction that I'm going to define for an invertible field theory, sorry, this should say a twisted spin invertible field theory, in dimensions 6 and below, is its projection onto the Q equals 3 layer, so the top layer. In general, projecting onto an arbitrary layer of the spectral sequence is not defined, but for a cohomological spectral sequence, you're allowed to project onto the top layer. And this is just the details of how it's constructed. So what you get is you get a homomorphism that looks like this. It takes your group of invertible field theories in dimension 5, and it produces a degree 2 z-valued cohomology class, and that's our obstruction. Okay, so I lied to you, but it's better that I did, because if the extension class B is not the second Stiefel class of a representation, this construction is a lot more complicated, and best to avoid that for now. But I'd be happy to talk about it at some point if you like. This does come up in some examples, but it's not. So here's a picture. You can see that we've got, so the diagonal lines represent the total degree. So this is total degree 5, 6, -1, 4, 1, 3, 2, 2, 3. So the extremal layer, the top layer, is the P plus IP. So we write it out, we take our bottom 3 and we say, those are okay. It's the red one that's the problem, the top one. So we want to show that if you have an invertible field theory and its P plus IP layer is non-zero, we'd like to obstruct there being a topological field theory with our assumptions with that in mind. So for now, let's turn off the twist just to simplify things. So I'm going to use the invertible field theory to define a group character. So from G to C star. So first, let's evaluate alpha on our old friend, the K3 surface. So that has a one-dimensional state space, and I'm just going to say that's isomorphic with Black's numbers. It is, so choose an isomorphism. So now, given any group element G, I can make the Bordism, which is K3 times the interval with trivial G bundle, but then I attach differently. So at 0, I attach by the identity. At 1, I attach by the group element. So this is the mapping torus for the action of my element. So these compose well. So this defines a homomorphism from G into C star, the value of this Bordism on alpha of K3. So I also have to tell you how to choose the spin structure. This is, we're going to want the one which, when you identify the boundary points, is the bounding spin structure. And I said, let's say B is 0. If B is not 0, you can do the same thing. It's just more annoying to prove that you can. So let's not worry about that right now. And again, I'd be happy to talk about it if this is something people care about. So what we proved, and I'll say a little bit more about this maybe depending on time, is that this character is non-zero if and only if the P plus IP layer is non-zero. And what Cordova and Omori proved, and they stated it for cyclic groups, but their argument goes through in general, is that the character is non-zero, implies that there cannot be a topological field theory with the things that we want and this anomaly. So we pass through the character to obtain the theory. And that those two steps give null existence. So in the interest of time, I'm not going to go into the details about the identification of a P plus IP layer and character. One way to do it is to stare at this and say, what does it really mean homotopically? We elected not to do that. It turns out that you can just reduce to the case of cyclic loops in one step. And then just there's only a few cases. It depends, like exactly how the spin Bordism groups look depends on the prime. And so you say, okay, well, what happens at P equals 2 with the twist, without the twist, what happens at P equals 3, and this equal should be a greater than equals because there are in fact more than 4 prime numbers, but 5 and on, they all behave the same way. So I apologize for this error. Okay, and so like I said, you just do the computation. It's not too bad. So the more interesting step is the one that is due to Cordova and Omori. So I want to briefly walk through their proof. What? I have 1 minute. Okay, I am not going to briefly walk through their proof. Please check out their paper. It's pretty cool. And like they do some topological field theory by decomposing K3 kinetic summits orientation rules, and that tells you that gives you a contradiction. So in the remaining, I guess, 45 seconds, I want to talk about what are the things that should happen next. The first one is a lot of the symmetries that people care about in quantum field theory for the application we have in mind are not finite. So, like the famous old SU2 anomaly, the new SU2 anomaly, what can we say about these? And the answer is we couldn't. We really, really needed G to be finite. And so progress would require generalizing quite a bit of the theory of fusion tube categories, and specifically Thibault and Matt's work, to incorporate these compactly grouped symmetries. I expect this to be difficult, but this would be very useful. Another generalization, which is closer to my heart, is anti-unitary symmetry. So what if I put this on something like a pin plus or a pin minus band? And so one specific example I think might be interesting to look at is the quaternion group, Q8, where I acts unitarily, J acts anti-unitarily. That determines the whole thing, and -1 is fermionic. So this thing has a Z mod 16 valued anomaly in 4 dimensions, meaning that the group of 5-dimensional IFTs is Z16. So it'd be cool to be able to say something about that. So we conjecture that you get the same story. We need to know better more about like unitary fusion tube categories. And the last thing I'll say, is it time? Okay, then I will not say the last thing, which is just it'd be nice to have examples, and that's all. So thank you all for your time. Sorry for going slightly over. Please let me know if you have any questions.
Question. Is the relationship between the character and your obstruction is he has a log map from
Which map?
Is it just like a boundary map from C star to Z? Yes.
Oh, that's a great question. We actually didn't check that. Like we got our theorem and then didn't go back and look at that. But I suspect that yeah. Is there a string Bordism version of these results? So what is the analog of fusion tube category with a twisted string symmetry? I think is the question to ask first, and I have no idea what that is. What? So the point is, a lot of the stuff I skated over that makes the existence result work is a huge library of work on fusion 2 categories corresponding to topological field theories with twisted spin structures. So, we have nice frameworks for representing twisted spin structures acting on stuff and like the algebraic and categorical data thereof. And so if you want to generalize to twisted string structures, like none of that's in place. It's probably hard. I've seen what people have been doing, making string structures geometric and like, in the sense, it seems really difficult. And then also on the physics side, what does it mean to have a G common W1, W2 lambda twisted string structure? It's like understanding that in concrete examples, the way that we understand twisted spin structures is an open question whose answer I would be very interested in learning, and it's probably also a prerequisite so you know what the right thing to prove is. Yeah, which is sad because I do like the board question. Yeah.
What do you think happens in other dimensions? I guess there's also an analog of people's ID in 6 dimensions.
Yeah, so the question is what happens in other dimensions? That's a great question. Okay, total guesswork right here, just to be clear. I think what we're going to find is that, so we don't have the fusion 2 category story there, but the obstruction is probably going to be very similar, and it may or may not tell you everything. Like, I feel like in this case, 2 things align nicely, and in other dimensions, my gut feeling is they'll still be there, but they might be they won't align. So you'll probably see something similar, but it's not going to be as tight of a field. Yeah, sadly.
Hey, thanks for speaker again. With you all tomorrow morning at 7:30. Sorry. You look your alarm.